So at each step, we need to prove that one statement implies the other. Let's start with 1 implies 2. So now we're only assuming that T is a tree, and we need to prove that T has no cycles and has precisely n-1 edges. Remember, n is the number of vertices. So since T is a tree, automatically it has no cycles by definition, and the theorem we just proved says that it has precisely n-1 edges. So we are done with this step. Next, we prove 2 implies 3. Now we don't assume that T is a tree or anything about T except that, according to statement number 2, it has no cycles and precisely n-1 edges. What we need to prove is that it is connected and has precisely n-1 edges. Well, the precisely n-1 edges is assumed, so the only thing we need to prove is that it's connected. If it is disconnected, it will have more than one component. Each component will have no cycles. So since now we have connected components, each component has no cycles, each component is a tree. Our graph is a forest. Since each component is a tree, the number of edges in each component is the number of vertices in that component minus 1. So we have an edge deficit of 1 in each component, meaning that in k components we will have a total edge deficit of k. Each component is missing 1 edge compared to the number of vertices, so k components will be missing k edges. But now suddenly we arrive to the conclusion that T has n-k edges with k greater than 1. This contradicts our assumption that we had precisely n-1 edges. Therefore, T cannot be disconnected, and we have proven that T is connected. Next, we prove that statement 3, which is that T is connected with precisely n-1 edges, implies statement 4, which is that T is connected and each edge is a bridge. So again, we need to prove connectedness, but we are assuming connectedness, so that's not hard to prove. We need to prove that each edge is a bridge. So again, remember, we are assuming that T is a graph with n edges, and the only thing we're assuming about T for this to work is that it is connected and has precisely n-1 edges. So we must prove that removing any edge disconnects T. That's what it means that every edge is a bridge. Well, we have previously seen in a theorem from some lectures ago, when estimating the edges of graphs, that a connected graph has at least n-1 edges. So if we start with a graph with n-1 edges and remove an edge, it will have n-2 edges, but this graph will be disconnected because of this edge estimate, because if it were connected, it would have at least n-1 edges. So if we start with a connected graph with precisely n-1 edges, removing any edge will disconnect the graph, and we have proved that each edge is a bridge. Next, we prove that statement 4 implies statement 5. Now you get the hang of how this is going. So we're only assuming that our graph T is connected and each edge is a bridge. We need to prove that the graph has no loops and that there is exactly one path between any two distinct vertices. And remember, bridge, meaning that removing the edge disconnects the graph. This is what we need to prove. So how do we prove that the graph has no loops? Well, if it had a loop, removing the loop will not do anything to the connectivity of the graph. So a loop cannot be a bridge, and therefore T cannot have loops because we're assuming that each edge is a bridge. So we need to prove that between any two distinct vertices, let's call them V and W, there is exactly one path. So we know there is at least one path because the graph is assumed to be connected. We need to prove that there are no more. But if there were more paths, then we would have a cycle, because we would have V here and W here, and maybe one path going somewhere and another path going somewhere else, and that would create a cycle. So therefore, there cannot exist more than one path. Why is that? Because if we have more than one path, that means we have cycles. But we're assuming that each edge is a bridge. And a bridge cannot lie in a cycle. Think about why this is. Pause the video if you want. So why can't a bridge lie in a cycle? Because any edge in a cycle, if you remove it, will not make the graph discontinuous. Because between the edges, between the vertices where your path went through this edge, since you are in a cycle, you might just as well go the other way around the cycle. So no bridge can lie in a cycle. Removing any edge of a cycle does not disconnect the graph. Therefore, if we have one more path, we contradict the statement that each edge is a bridge, and this proves that statement 4 implies statement 5. Next, we prove that statement 5 implies statement 6. So now we're assuming about our graph T that it has no loops and that it has exactly one path between any two distinct vertices. What we need to prove is that it has no cycle and that adding any edge will create precisely one cycle. So first we need to prove that T has no cycle. If T had a cycle, where would this cycle be? Either it would be a loop, but we're assuming we don't have loops, so that can't happen. Or we would have our cycle having at least two vertices lying on it. So we might have a cycle of this kind. But if we have a cycle with two distinct vertices on the cycle, then this means that we will have two paths between these vertices, either this upper path or the lower path. And since we are assuming that there is exactly one path between any two distinct vertices, that can't happen either. So there cannot be a cycle. Next, we want to prove that adding an edge will create a cycle. So if the edge that we add is a loop, then the loop itself a cycle, and we have created a cycle. If the edge we add is incident to two different vertices, then since there was, by assumption, already one path between these two distinct vertices, adding this edge will create a cycle. So the situation is this: we have V and W. We assume that there is one path between them, something like this. And now if we add an edge, you see that we're creating a cycle. So we have proved that adding an edge, whether it's a loop or not, creates precisely one cycle. It creates at least one cycle. Now we need to prove that adding an edge doesn't create any more than two cycles. So assume it does. Assume that several cycles are created by adding this edge E. Then each of these cycles must contain our edge E. Think and pause why this is the case. Well, the reason is that in our graph, we had no cycles because we had exactly one path between two distinct vertices. So since our original graph has no cycles, all the cycles that can be when we add the edge E must contain the edge E, because a cycle without the edge E is the same thing as a cycle that was there from the beginning, and we don't have those. Then you can prove, this is an exercise in the book that you might not have done yet, but for now, let's just accept this as true. You can prove that if you have in a graph two cycles that contain an edge, then you can create a cycle that does not contain the edge. Let me sketch the proof. If you want to prove it thoroughly, I encourage you to do this exercise. So assume we have this edge E that lies on not only one, but two cycles. Then, roughly speaking, what you do is you start with one vertex, or with one edge of E, and go along one cycle until you come back to the other vertex of E, then you go along the other cycle. Of course, this is a special case. It might be that the two cycles share more than the edge E, and then you have to prove that more thoroughly. But that's the general idea. If you have two cycles that contain the same edge, then in the same graph, you also have one cycle that doesn't contain the edge. But a cycle that doesn't contain the edge, by what I just said, means that you have a cycle in the graph from the beginning. And that's a contradiction. So this is the longest part of the proof. So the proof was in 3 parts. We proved that it has exactly one cycle, that adding an edge creates a cycle, and that adding an edge creates precisely one, meaning no more than one cycle. And these steps altogether prove that if we just assume that the graph has no loops and exactly one path between any two distinct vertices, then it follows that T has no cycle and that adding any edge creates precisely one cycle. Finally, we need to prove that our statement 6 implies statement 1. So statement 6 is this long statement that T has no cycle and adding any edge creates precisely one cycle. We need to prove that such a graph is a tree. So since we're already assuming that T has no cycle, the definition of tree, that the tree is a graph with no cycles and that is connected, all that remains to be shown is that T is connected. If T is not connected, then T has multiple components. Say we have some component here that looks somehow, and some other component here that looks in some other way. And now, if we add an edge between these two components, this edge will be a bridge. Why is it a bridge? Well, a bridge is an edge whose removal disconnects the graph. So if we added this edge and now we connected these two components together, if we remove the edge, the graph will again be disconnected. So this edge is a bridge, and by what we just said, a bridge cannot be part of a cycle, so this contradicts the fact that any added edge creates a cycle. So if T indeed satisfies that property, then T must be a tree. That was a long proof that consisted of many steps, so go back if you need, write it down, look at the notes. But what we have proved now is that this cycle of implications hold, and therefore these 6 statements are equivalent. So for example, you can, if you want to check that a graph T is a tree, it's enough to check that T is connected and each edge is a bridge. In some contexts, this might be the easiest definition to check.